Okay, so this is a bit of a transition. We're going to be spending a little more time on Python, but we also have to do some stuff manually. So I hope that you enjoy the shift towards more Python work. The last worksheet was entirely manual and review, and I hope that you found it helpful. This one is basically Python, and it should start with a review and build into some new areas. So here we build a small bit of code to support some linear algebra functions, and then we're going to move over to some pre-built tools which are more robust and faster and so forth. Okay, to answer the first few questions on the worksheet, you're going to need to write your own code. So you're going to really want to essentially reduce a matrix. Okay, so for example, I want you to write swap rows that takes in a matrix, an A and a B, and it should work on M directly. Okay, and it will just be lists of lists. So for example, maybe you have M is equal to a list of lists, okay, so if I had something like this in Python, then if I did swap rows of M02, for example, I would expect that this would cause 2 rows to swap. So this is what you're imagining in your head. M is 1, 2, 3, 4, 5, 6, 7, 8, 10. Okay, I don't make it 7, 8, 9 because then they'd be linearly dependent and that would be a pain. So if I'm wanting to swap these guys out with these guys, then this is how I would do it. Okay, and so that would be the effect you'd expect to see, and if you type M in Python, you would find that you swapped index row with index 0 with row with index 3. Okay, but in order to do that, you're going to have to write some other things first. You have to figure out how you're going to do that. Actually, this one should be pretty straightforward. It should only take a couple lines of code. If I had another function that's called, let's say, scale row MAT, then it should do what you would expect. So if I said scale M let me just go look that up for a sec. I just wanted to make sure I didn't swap the role of A and T on you. Okay, so if I scale row 1, which is the second row, right, because we're counting in Python, by a factor of 10, what I'm going to get is this is going to turn into 40, 50, 60 right here. Okay, and that's going to update that row. The function I want you to write combine rows does not work directly on M itself. So in that case, let's say I said combine rows M0, -4, 1, 1. What does all that garbage mean? Well, that means I'm going to take in M, which currently is in this state, and I'm going to take -4 copies of row 0 and 1 copy of row 1, and I'm going to add them together. And I'm going to actually just return this list of values. Okay, and then it will return, in this case, 12, 18, 20. So how does it calculate it in there? Let's just double check that I did this right. So it takes -4 copies of the first row, so it should be -28, -32, -40, and it adds it to 1 copy of the next row. And in this case, we should get 20, 18, 12. At least if I did that right. Okay. Okay, but once you have those working, you can easily do something like this. You can easily say something like M1 equals combine rows M0, -4, 1, 1. So because you're working on a computer, this is not a math equation, the first thing you do is you calculate this part, and that gives you 12, 18, 20. Okay, now that's going to go directly over to our matrix, which lives over here. And I'm going to put it in position M1, so it's going to get rid of whatever's there. It's going to replace it with 12, 18, 20. Okay, so these things become quite powerful, and then they build on each other. And finally, so the final thing I want you to write is reduce M. And I'm going to leave it to you to figure that out, but we're going to do sort of like a slow walkthrough of a solution based on the technique that I expect you to use. If you take a few liberties, that's okay, as long as you hit the major goals as we go through. And I'll explain that as we go through the slow walk on a simple matrix. I'll talk about what I'm doing and what I'm calling everything, and so I'll tell you where you have to make sure to hit those goals, okay? But reduce M, once you get it working, it does all the work and it calls all those other functions to help with the work, okay? Don't make the assumption that your matrix is necessarily square, but you know, maybe it is. Okay, so we're going to slow walk this solution here. Okay, so first of all, if you have this problem, x's, y's, z's, and w's, and you're trying to find from 4 equations, you're looking for 4 unknowns, your first job is going to be to convert to a matrix. I wanted to write out the equations this way at least once so I can sort of drive home this point that this is exactly the same problem as what we get with the matrix, which looks like this. So the first step is step 1. I want to make sure that this guy is not equal to 0. So element 0, 0 is not equal to 0. Now, if it is, you need to do something to swap. You need to swap with a row below, so it's not equal to 0. Or check to make sure all below equals 0. So the point is, if there's nothing below that position, which is non-zero, then you can't swap to solve the problem, and then you go to the next stage in the solution process. But if there's something below that position which is non-zero, you're going to have to swap so that you can attempt to make that position in that circle equal to a non-zero element. Okay, and so now I'm going to scale it, step 2, so that it becomes 1. So step 2, scale this row so item in the circle becomes 1. In this case, it's already done. Step 1 and step 2 are completely done, and so we're done. I'm going to feel free to erase stuff whenever I want because you have a video and you can rewind it. I've kind of been doing that to you all year anyway. Step 3, everything in this column, you want to scale it so it's equal to 1 or 0. If it's 0, you can leave it alone. Okay? So what I'm going to do is I'm going to scale all this stuff, and I'm going to do this in such a way that hopefully it's not scary. So I'm going to just make a copy actually, so that we don't forget where we came from, because I'm going to have to erase stuff and write it back in again. Okay, so what are we going to do to put the second row back in? We're going to divide by 2. Okay, and then what about the next row? We're going to have to divide that off by 3. Okay, and then the last row we're just going to have to switch the signs. So any pluses kind of look dorky, so I'm going to get rid of them. And that looks like what I expected. So now I'm going to get rid of the other matrix that no longer exists. Okay, at this point in the process, we've now dealt with the first row, and we're going to do a subtraction of sorts so that these guys all become zeros. Again, any elements that are already 0, we can just leave that row alone. In this case, okay, deal with all rows having 1 under this element that has a circle, that circled element. If it's 0, ignore. At this point you should only have 0s and 1s. So what I'm going to do is I'm going to do a subtraction, and there's more than one way you can do this. You can if I label these A, B, C, D, I can go like A minus B and put it in B's position, or B minus A and put it in B's position. Okay, so you have a couple different ways that you can choose to do that, but the object of the game is to, at this point, turn all these guys into zeros. So we're going to do that. We're going to copy this so we don't forget where we came from. And we know that all these are going to turn into zeros. So what's going to happen? We're going to have something like 1, 1, 0, 3, 4, and we're going to subtract 1, subtract a half, add a half, subtract a half, subtract a half. So again, I don't care which one you subtract from which one, but when you're done, you're getting something like this. Let's make sure you don't flip halfway through a calculation though. So 1 plus negative a half is 1/2. I've set this up so I'm adding, what's 3 1/2? 7/2, okay? And so I'm making this 0, 1/2, 1/2, 5/2, 7/2. Okay then. So I'm going to do something similar for row 2 and 3. I'm going to do like, let's do this again, 1, 1, 0, 3, 4, and I'm going to subtract row C. So I'm going to multiply by -1, so then I can just add. Gosh, 3 is 9/3, so I have 7/3 here. Okay, and I'm going to copy this down. Alright, and so then what's going to happen here is I have to deal with the last one. I have 1, -1, 2, 3, -1, and +4. So I don't need the 9/3 this time. I get 3, 3, 2, 8 this time. Alrighty then. So I've now gotten rid of all this junk, and I'm on to the next step. The next step is going to look very much like what we just did, because now we're essentially going to run the same algorithm we were running before, but now on a smaller rectangle or square. Okay, so we had originally highlighted this pivot element, and now we're going to pick a different one on the diagonal as our new pivot element, and it is non-zero, so I am happy. And my goal is to now scale, so that is 1 and everything below it is 1. So I'm going to go ahead and do another copy here, just for good good measure. How do I turn that into a 1? Well, I just double everything. Not hard. What about the next one? Oh, what a pain. 4/3 times 3/4. So 1/3 times 3/4. 7/3 times 3/4. And 5 times 3/4 is going to be all those magic numbers we need for this row. And so let's go ahead and do that. That's going to be 1, 1/4, 7/4, and 15/4. 15/4, if you prefer, you can write 3.75. I don't care. It's up to you. Okay, these all need to be divided by 3. So it's going to be bing, bing, 2/3, 8/3. Again, you can use decimals if they are exact. It's not easy to do with thirds. Okay, now we're going to have to do some more subtraction. And again, we're going to have to look at all the items below this pivot item, all those elements, and if they're not zeros, they should be 1s now. And now we need to turn them into zeros. So now we're looking at 0, 1, 1, 5, 7, and we're going to flip the sign of row C. 0, -1, -1/4, -7/4, and I'm just going to write it as 3.75. Let's see how this works. 0, 0, 1 minus 1/4 is 3/4 or 0.75. 5 minus 7/4, gosh, 7/4 is almost 8. -1.75, so it's going to be like 5 minus 2, which is 3 plus 1/4, so I think 3.25 looks right. And 7 minus 3.75 should be 3.25, I believe. Let me just double check this. Yeah, it looks good enough to me. Okay, so I'm going to get rid of these guys and replace it with 0, 0, 0.75, 3.25, 3.25, and I'm going to do something similar on the next row. I know. Why don't you tell me what the next row should be? Pause the video and you tell me. Okay, so I'm going to take the I guess I'm not going to take the liberty of reducing this. If I were doing this by hand, I'd just automatically replace this with a 1 and a 1, but I'm trying to simulate what your computer algorithm should be doing. So at this point in the process, we've successfully wiped out everything below our pivot element. Everything below that is a 0, and then we're going to go on to our next pivot item, which is, of course, the next thing in the diagonal, which right now is sitting at a 0.75, which is just kind of annoying. But we're going to have to rescale that so that it's 1. And notice, yes, we got a free 0. That was just a fluke. So that'll make our life easier. But anyway, let's rescale this so that the 0.75 becomes 1. Okay, hopefully this is what you got. And finally, when you select this guy as being your last pivot, because you're running out, like you don't have any more rows, at this point, when you do your scaling, then this is all going to become just ones. Okay, this is your halfway point. And this is, you've actually done all the hard work if you arrive here successfully. Now what we want to do is backward substitution. Back or back substitution. Backward substitution, back substitution. I've heard it both ways. Back substitution. Okay, so when you're doing backward substitution, you're going to follow the same pivot positions, but you're going to do something different with it. So you're going to use this, there's ones on the diagonal, and you're going to use that fact to wipe all these guys out that are in the rectangle. They all have to become zeros. But it goes with whatever it's next to. So for example, in this case, it's very easy. This is like saying W equals 1. Okay, we've got the first part of our solution, and so it allows us to go back and wipe out equal parts. So like this guy wipes out, so you get zeros here. That was just lucky. Here you can wipe out 5 here as long as you wipe out 5 of the 7, so you're left with 2. You can wipe out 3 W's as long as you wipe out 3 units, and then so you've got zeros all the way up. Okay, and then you just move your pivot backwards, so your pivot just moves back in the opposite way it came down. This is very bizarre. This is saying z equals 0. So it means, honestly, this actually is pointless. I can just, like, what can I do? I can just get rid of it. And it doesn't change the 2 at all. It says I can actually get rid of it for free. So that was weird. And now I move the pivot up. And what does this say? This says, how come I didn't move this? Okay, there we go. This says that now y equals 2, so I can get rid of y if I get rid of 2. Right? So I only have one y to get rid of. I subtract 2, and this brings me down to -1. At this point, I have ones on the diagonal, and I have completely solved this. So relative to our original question, we have x equals -1, y equals 2, right? Z equals 0, and w equals 1. And we have this lovely thing over here that's called an identity matrix. It doesn't want to be lovely today. Okay, this is I sub 4. This is our identity matrix, and this is our answer. Yay! Okay, so that is the process, and so let's talk about this same thing a different way. Let me set up. Okay. So we can write the matrix M as a 2 by 2 grid, and we have what's called a vector B, which is a column vector, and in this case we say mx equals b, and we say please solve for b. Please find x that solves this problem. All right, and so what we want to do is we want to do this kind of thing. We would like to find M inverse. I mean, this is one of many ways you can talk about it. So that if you multiply M inverse on both sides of this equation, so you see, let me just color code this thing. The black stuff is what we had before, and now the blue stuff is multiplied on the left, and of course this is matrix multiplication, so left and right multiplication are different. But we have this magical thing. Whoa, that's not what I wanted to do. This thing turns into identity matrix, so this would be x equals M inverse b. So if only we can find m inverse, then all you have to do is multiply it to the left of b and you get x automatically. Okay, so you can actually do that in Python. There's like several different ways of solving this in Python. So let's pull out Python and do a couple tricks and start getting used to that. Okay, so I'm going to always start with two things. From math, import star. Yes, it's cheesy, and yes, I do it, and yes, you're allowed to. Import Numpy as MP. That's not cheesy. That's what everyone does, and that's what you're expected to do. Okay, so now instead of using the arrays the way we did, I'm going to use the actual Numpy array so that I can do cool stuff with it. Okay, so 1, 1, 0, 3, 2, 1, minus 1, 1, 3, minus 1, minus 1, 2, minus 1, 2, 3, minus 1. And b, oh, well, let's go ahead and put b in here. Numpy is really forgiving because I technically should have to transpose this, and some computer algebra systems would yell at you for not transposing it. So if I do want to transpose it, I can do .t if I want to, but it's actually just displaying the same thing because it's polite. It doesn't want to jam up my screen, but I can. Let me just show you on M. So notice if I do M and M transpose, it shows you the transpose version of M. Okay, but what we really want is the inverse. Yay, isn't that cool? So I can do this. M inverse equals NP ln alg inverse M. So now I've got a permanent copy of M inverse and a permanent copy of M. And now if I want to just multiply, I can go M inverse times, and I use this funny @ symbol to do that, B. And of course I can do B transpose. And again, this is just because Numpy is being extremely forgiving about how I feed it B. I'm really happy because I'm just used to computer algebra systems choking when I give it B in the wrong direction. So Numpy is very, very sweet this way. Very, very happy. So I have a solution here, and it's telling me x is -1, y is 2, z, I want you to notice z is 0. So notice because it says times times 10 to the power of -16 is what it's saying, and then w is 1. So notice these other points here, the solutions are times 10 to the 0 or 1, right? So you have to be aware when you're looking at all this output, which we're going to do a lot of, if there's an e to the -16 or e to the -17, definitely just treat that whole number as a 0 because it's round off error. We don't want to worry about that. We just want to assume that's 0 for the purposes of what we're doing. Okay. So the purpose of this assignment is not to just get it to work once, but I want you to play around with it. I want you to use these tools I've just given you. And there are more tools, and I will show you soon. But I want you to just play with these basic tools to start off with, and I want you to try different things. One thing you can do is you can just Google other homework assignments. Like there's courses all over the world for linear algebra or numerical analysis. Just find some homework that's somebody's homework they're supposed to do by hand, and see if there's an answer key somewhere. And then just try something and see if it works. By the way, the solve command is the preferred way to solve. You don't usually find the inverse matrix first, so I may as well give that to you. Then alg solve MB. And so that's the quick and easy way to solve. You don't usually find M inverse and multiply it by Yeah, you don't normally do that. But for these exercises that you have, they're so small, they're so fast, you can do them either way, and I just want you to have fun playing with them and getting used to it. Okay? So for these exercises in this worksheet, anything you do with Numpy is fine with me. I just want you to get comfortable with it. Okay? See you soon.